Hello, Algebra 3. It's Mr. Brock. This is the current, right now, this year, 2025, Mr. Brock. But much like last week, we have testing this week on Tuesday, so we are not having class. So I have dug back into the archives and I pulled out 2024, Mr. Brock, and I said, Mr. Brock, could you come help us this year in 2025 and give us the lesson for the week? So, past Mr. Brock has graciously agreed to step in and fill in for current Mr. Brock, who's going to be busy with all this testing today. So here you go, guys. Thursday and Friday are both B days this week. So if you're struggling with any of this, please come to class on Thursday and Friday. Of course, if your grade's below 70%, I'll see you anyway. But come see me, and I can help you if Mr. 2024 Brock is confusing in any way. But all right, here we go. Let's take a look.
Hey, I got to brag on this class while I'm here. We've got to look at this week's lessons. We've got 3 videos today, 3 videos on matrices. And we have 4 assignments. So let's take a look at that. Let's go to our grade screen as usual. And if we scroll down, we will see April 14th. That's this Sunday. We've got to do a determinant of a 2x2 matrix. It's not hard. You just pay attention. And then we're going to do inverses. Introduction to matrix inverses. We're going to talk about determining what the inverse is, and how to determine if the matrix even has an inverse. So not every matrix has an inverse. So we have to be able to determine which ones do and which ones don't. So these are the 3, and these are all related. The determinant is used to find the inverse. So we'll do these 3 assignments, and then we will do the quiz. So that's what we have this week. 3 assignments of the quiz. There's 1 video to go with each of these assignments. So we will look at those 3 videos in class here today. Then you have the 3 assignments and the quiz. And then next week we have 2 assignments and a quiz, and we'll be done with matrices. So 1 more week after this of matrices. So let's go back and see what we have. See, we can close the addition and scalar multiplication. We can close multiplying matrices by matrices. Quiz 2 is what we did last week, so we start right after that. So we have quiz 2. This week we have these 2 folders and quiz 3. So it's a nice way to figure out where we're at on this, since I don't have everything with numbers on it this time. So determinant. There we go. We have our video lesson and our assignment right there. So let's take a look at the video lessons.
As a hint, I'll take the determinant of a very similar 2x2 matrix. So we want to figure out the determinant of this matrix, and we can denote it by the determinant of the 2x2 matrix 5, 3, -1, and 4. And the definition of a determinant of a 2x2 matrix like this is we can first take this diagonal, 5 times 4. So let me write that down. So it's going to be 5, it's going to be equal to 5 times 4 minus the product of this diagonal, minus the product of that diagonal. So minus 3 times -1. 3 times -1. So what does this give us? So 5 times 4 is 20. And then 3 times -1 would be -3. This is -3. But then we're subtracting -3, which would make it adding a +3. So 20 plus 3. And so the determinant of this matrix, ready for the drum roll, is 20 plus 3 is 23.
All right. Pretty short, pretty sweet right there. How to find the determinant. Here, let me go over that again. just to give us a little bit more of a look at it. All right, so if we have this matrix A, and I've just put A, B, C, D, just show you, it doesn't matter what the numbers are, because the determinant works the same way every time. As he was showing us, to find the determinant, you multiply A and D, whatever those two numbers are, and then you subtract B and C, whatever those are, when you multiply those together. So the determinant, we write the determinant like this. You put the absolute value symbol on the side. The determinant of this would be A times D minus B times C. That's what the determinant equals. A times D minus B times C. I'm like, oh, okay. Well, let's take that a step farther and do it with an example. So let's do this matrix B, and let's actually give it some numbers. So it's going to be -2 and 4, and we'll say -1 and 8. So we gave it, now let's have an actual matrix with some numbers in there. So the determinant, which another way you can say the determinant is like that. All right, so it's going to equal these two first, -2 times 8 minus 4 times -1. Well, -2 times 8 is -16 minus -4, which means we're adding it. So the determinant is -12. Because -16 plus 4 is -12. So the big thing, no matter what, and we're only looking at 2x2 matrices for determinants. It gets really tricky when we're doing some bigger than that. So we're only going to look at 2x2s, make that easy on us. But this is the key thing you have to figure out. Just A times D minus B times C. That's it. We're going to look at some more videos today where he starts talking about the vectors and all the other things when we find inverses. The main thing is, do you know how to find the determinant? Because it's going to be really big with inverses. It's going to decide everything with inverses. So don't make this complicated. It really is very simple. Multiply diagonally and then multiply diagonally and subtract those. Right? That doesn't seem too bad, right? I think we can do that. So let's look at, let's close that one out. Let's look at the assignment that goes with this. Here's our first assignment. It's one of these where we copy and paste our score. So let's click on the assignment and take a look at finding the determinant. Close that window. There you go. What is the determinant of C? Diagonally, -1 times 2 is -2. -2 minus 2 times -2. Well, that's -4. So -2 minus -4. Well, if we're subtracting -4, that means we're adding 4. So -2 plus 4, the determinant's just 2. Let's check. Nice work. We got it. See, I'm on problem number 3 because I did a couple of these already. Next question. What's the determinant of D? -1 times -1. Well, that's just 1. And then we subtract 3 times 4. So 1 minus 12 minus 11. Fabulous. Look at there. It says I got 3 out of 3, but the last screen said I had 4 out of 4. That's just kind of weird. So I would take that, screenshot it, turn it in, say, okay, I got my work done. All right, let's go back and look at our next thing here. Okay, so that's the determinant. And remember, we need to know how to do that for the inverses that we're about to look at now. All right, let's look at our intro to matrix inverses. And just realize when he starts talking about vectors, and we'll get to vectors. I mean, we'll take a look at vectors real quick. A vector on a graph is usually, it starts at the origin, and if we have a point over here, a vector would be from the origin to that point. That's a vector. A vector has direction and distance. It goes that direction that long. So we're not really, hadn't really studied vectors, but I just want you to understand what he's talking about when he talks about a vector. So, this would be based on if this is 6 and this is 3. We could figure out the length of that vector by using the Pythagorean theorem, knowing that this is a distance of 6 and that's 3. But we're not going to be getting into vectors. I just don't want you to be confused when he starts talking about that. He's just talking about something that has a direction and a length from the origin. And when he multiplies matrices together, he's talking about multiplying two vectors. Like this would be the vector 6, 3. See, because it goes to 6, 3. That's where the vector starts at the origin and goes to the X and the Y. So don't get confused about that. Focus on this part. The determinant is a big part of it. So it can get a little tricky with inverses. So that's why we're not going to go very deep into inverses, because we're going to do inverses of 2 by 2 matrices. If we did 4 by 4 matrices, it would take us an hour to do it. And anything bigger than that, we'd want a computer to do it, because inverses can be quite lengthy. So that's why we're going to stick with a 2 by 2. It's not bad with a 2 by 2. So let me, again, change how I share this back. I got to go back and forth and remember to do this properly so you can hear the videos and see the other things that we're showing you. All right, maximize. All right, this ought to be good.
We've learned about matrix addition, matrix subtraction, matrix multiplication, so you might be wondering, is there the equivalent of matrix division? And before we get into that, let me introduce some concepts to you, and then we'll see that there is something that maybe isn't exactly division, but it's analogous to it. So before we introduce that, I'm going to introduce you to the concept of an identity matrix. So an identity matrix is a matrix, and I'll denote that by capital I. When I multiply it times another matrix, actually, I don't know if I should write that dot there. But anyway, when I multiply it times another matrix, I get that other matrix. Or when I multiply that matrix times the identity matrix, I get the matrix again. And it's important.
All right, I'm going to pause it right there just to remind you, we did identity matrices. That's a past week that we did, right? And that just means you're multiplying a matrix by 1. Remember? Because that's what the identity matrix was, multiplying by 1. So that's why if you have an identity matrix times A, which is a matrix, you'll end up with just A because you multiplied the matrix times 1. So he reviews that a little bit here, talking about multiplying that identity matrix. And that's going to be important with inverses, just to remember that the identity matrix exists. And what it is, it's that matrix that just ends up like multiplying by 1.
Important to realize when we're doing matrix multiplication that direction matters. So it's actually, I've actually given you some information here that, we can't just assume when we were doing regular multiplication that, A times B is always equal to B times A. It's important when we're doing matrix multiplication to kind of confirm that it matters what direction you do the multiplication in. But anyway, and actually I just want to make sure this works both ways, only if we're dealing with square matrices. It can work in one direction or another if this matrix is non-square, but it won't work in both. And you can think about that just in terms of how we learned matrix multiplication, why that happens. But anyway, I've defined this matrix. Now what does this matrix actually look like? It's actually pretty simple. If we have a 2 by 2 matrix, the identity matrix is 1, 0, 0, 1. If you want 3 by 3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. I think you see the pattern. If you want a 4 by 4, the identity matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So you can see all the identity matrix is for a given dimension. I mean, we could extend this to an n by n matrix, is that you just have ones along this top left to bottom right diagonals, and everything else is a 0. So I've told you that. Let's prove that it actually works. So let's take this matrix and multiply it times another matrix and confirm that that matrix doesn't change. So if we take 1, 0, 0, 1, now let's multiply it times, let's do a general matrix, just so you see that this works for all numbers, A, B, C, D. So what does that equal? 1 times, so we're going to multiply this row times this column. 1 times A plus 0 times C is A. Then that row times this column. 1 times B plus 0 times D, that's B. Then this row times this column. 0 times A plus 1 times C is C. Then finally this row times this column. 0 times B plus 1 times D, well, that's just D. There you have it. And it might be a fun exercise to try it the other way around as well. And I think and actually it's an even better exercise to try this with a 3 by 3. And you'll see it all works out. And a good exercise for you is to kind of think about why it works. And if you think about it, it's because you're getting your row information from here and your column information from here. And essentially, anytime you're multiplying, let's say, this vector times this vector, you're multiplying the corresponding terms and then adding them, right? So if you have a 1 and a 0, this 0 is going to cancel out anything but the first term in this column vector. So that's why you're just left with A. And that's why it's going to cancel out everything but the first term in this column vector. And that's why you're left with just B. And similarly, this will cancel out everything but the second term. So that's why you're left with just C there. Right? This times this, you're just left with C. This times this, you're just left with D. And that same thing applies when you go to 3 by 3 or n by n vectors. So that's interesting. You have the identity vector. Now, if we wanted to complete our analogy, so let's think about it. We know in regular mathematics, if I have 1 times A, I get A. And we also know that 1 over A times A, this is just regular math. This has nothing to do with matrices, is equal to 1. Right? So, and we call this the inverse of A. And that's also the same thing as dividing by the number A. Right? So is there a matrix analogy? Is there a matrix, and let me switch colors because I've used this green a little bit too much. Is there a matrix where if I have the matrix A and I multiply it by this matrix, and I'll call that the inverse of A, is there a matrix where I am left with not the number 1, but I'm left with kind of the 1 equivalent in the matrix world, where I'm left with the identity matrix? And it would be extra nice if I could actually switch this multiplication around. So A times A inverse should also be equal to the identity matrix. And if you think about it, if both of these things are true, then they're actually, not only is A inverse the inverse of A, but A is also the inverse of A inverse. So they're each other's inverses. That's all I meant to say. And it turns out there is such a matrix. It's called the inverse of A, as I've said 3 times already. And I will now show you how to calculate it. So let's do that. And we'll see calculating it for a 2 by 2 is fairly straightforward, although you might think it's a little mysterious as to how people came up with the mechanics of it or the algorithm for it. 3 by 3 becomes a little hairy. 4 by 4 will take you all day. 5 by 5, well, you're almost definitely going to do a careless mistake if you did the inverse of a 5 by 5 matrix, and that's better left to a computer. But anyway, how do we calculate the matrix? So let's do that, and then we'll confirm that it really is the inverse. So if I have a matrix A, and that is, let's just say A, B, C, D, and I want to calculate its inverse is actually, and this is going to seem like voodoo, and in future videos I will give you a little bit more intuition for why this works. I'll actually show you how this came about. But for now, it's almost better just to memorize the steps, just so you have the confidence that you know that you can calculate an inverse. It's equal to 1 over this number times this, A times D minus B times C. A, D minus BC. And this quantity down here, AD minus BC, we'll learn soon, has a special, well, actually, we don't have to learn it soon. That's called the determinant of the matrix A. And we're going to multiply that. And so this is just a number, right? This is just a scalar quantity. And we're going to multiply that by, you switch the A and the D, you switch the top left and the bottom right. So you're left with D and A. And you make these two you make the bottom left and the top right, you make them negative. So minus c and minus b. And the determinant, and once again, this is something that you're just going to have to take a little bit on faith right now. In future videos, I promise to give you more intuition. But it's actually kind of sophisticated to learn what the determinant is. And if you're doing this in your high school class, you kind of just have to know how to calculate it, although I don't like telling you that. So what is this? So this is also called the determinant of A. So you might see on an exam, figure out the determinant of A. So that, let me just tell you that. And that's denoted by A in kind of absolute value signs. And that's equal to AD minus BC. So another way of saying this could be 1 over the determinant. So you could write A inverse is equal to 1 over the determinant of A times D minus B minus C A. Any way you look at it, but let's apply this to a real problem, and you'll see that it's actually not so bad. So let's say that I have a matrix. Let's change letters, just so you know that it doesn't always have to be an A. Let's say I have a matrix B, and the matrix B is 3. I'm just going to pick random numbers. Minus 4, 2, minus 5. Let's calculate B inverse. So B inverse is going to be equal 1 over the determinant of B. What's the determinant? It's 3 times minus 5 minus 2 times minus 4. So 3 times minus 5 is minus 15. Minus 2 times minus 4. So 2 times minus 4 is minus 8, but we're going to subtract that, so it's plus 8. Plus 8. And we're going to multiply that times what? Well, we switch these two terms, so it's minus 5 and 3, and we just make these two terms negative. Minus 2 and 4, right? 4 is minus 4, so now it becomes 4. And let's see if we can simplify this a little bit. So B inverse is equal to, it's minus 15 plus 8, that's minus 7, so this is minus 1/7. So the determinant of B, we could write B's determinant is equal to minus 7. So it's minus 1/7 times minus 5, 4, minus 2, 3, which is equal to, this is just a scalar, this is just a number, so we multiply it times each of the elements. So that is equal to minus plus, so it's 5/7. 5/7 minus 4/7. See, positive 2/7, 2/7, and then minus 3/7. Minus 3/7. It's a little hairy. We ended up with fractions in here and things. But let's confirm that this really is the inverse of the matrix B. Let's multiply them out. So before I do that, I should create some space. Create some space here. I don't even need this anymore. There you go. Okay, so let's confirm that that times this, or this times that, is really equal to the identity matrix. So let's do that. So let me switch colors. So B inverse is 5/7, if I haven't made any careless mistakes, minus 4/7, 2/7, minus 3/7. That's B inverse, and let me multiply that by B. 3 minus 4, 2 minus 5. Now this is going to be the product matrix. I need some space to do my calculations. So let's see. First I'm going to take this. Let me switch colors. I'm going to take this row times this column. So 5/7 times 3 is what? 15/7. 15/7 plus minus 4/7 times 2. So minus 4/7 times 2 is, it's minus, let me make sure that's right. 5 times 3 is 15/7. Minus 4, oh yeah, right. 4 times 2 is so minus 8/7. Minus 8/7. Now we're going to multiply this row times this column. So 5 times minus 4 is minus 20 over 7. So minus 20 over 7 plus minus 4. Right, so minus 4 sevenths times minus 5. That is plus 20 over 7. Plus 20 over 7. My brain is starting to slow down, having to do matrix multiplications with fractions with negative numbers. But this is a good exercise for multiple parts of the brain. But anyway, so let's go down and do this term. So now we're going to multiply this row times this column. So 2 sevenths times 3 is 6 sevenths plus minus 3 sevenths times 2. So that's minus 6 sevenths. One term left, home stretch. 2 sevenths times minus 4 is minus 8 sevenths. Minus 8 sevenths, right? 2 sevenths times 4 is minus 8 sevenths. Plus minus 3 sevenths times minus 5. So those negatives cancel out, and we're left with plus 15 over 7. 15 over 7. And if we simplify, what do we get? 15 sevenths minus 8 sevenths is 7 sevenths. Well, that's just 1. This is 0, clearly. This is 0. 6 sevenths minus 6 sevenths is 0. And then minus 8 sevenths plus 15 sevenths, that's 7 sevenths. That's 1 again. And there you have it. We have actually managed to inverse this matrix. And it actually, as you see, it was actually harder to prove that it was the inverse by multiplying it, just because we had to do all this fraction and negative number math. But hopefully that satisfies you, and you could try it the other way around to confirm that if you multiply it the other way, you'd also get the identity matrix. But anyway, that is how you calculate the inverse of a 2 by 2. And as we'll see in the next video, calculating by the inverse of a 3 by 3 matrix is even more fun. See you soon.
Okay, you're like, wow, that kind of blew my mind. Well, the more you practice this, the easier it gets. So this is definitely something you need to do with pencil and paper. You're not going to do this in your head, but let's look at the assignment that goes with this and see if we can practice some of this. We need to practice this together so that we are on the same page here. So here's the assignment that goes with it, determining inverse matrices. So we're going to take a look at that and see what kind of problems it has for us. Because when I was looking at this yesterday, some of these problems are a little different than what he just showed. Okay. Here they've given us, we're not calculating what the inverse is. That's not the problems they're giving us. They're giving us a matrix and another matrix, and they're saying, are they inverses? So is matrix B the inverse of matrix A? Well, the only way to know that is to multiply them together and see, do we end up with the identity matrix, right? If we don't end up with the identity matrix, they must not be inverses, because what his video was showing us is that you have a matrix and its inverse, and you multiply them together, you should end up with the identity matrix. So we're going to do this one together. So I'm going to write it down here. And we're going to review multiplying with fractions again, because it's probably been a while since you've done that. We're going to multiply these two matrices together. That was A and this is B. And if they end up being the identity matrix, which remember the identity matrix is 1, 0, 0, 1 for a 2 by 2. Which, by the way, I put in my notes. You should have in your notes how to find the determinant, which I jumped the gun. You don't do the little -1. -1 is for inverse. How to find the determinant, and then how to find the inverse. So I put this in my notes. The inverse, which that's what the -1 is. A -1 is the inverse. 1 over the determinant, all right? The determinant is found like that, times, look, A and D trade places. They trade places. And B and C stay where they are, but they become the opposite sign. So this is how you find the inverse. 1 over the determinant times the matrix rearranged. D and A, B and C. So this is great for your notes. And if we multiply A times its inverse, we'll get the determinant the identity matrix.
If we multiply this and don't get that, these are not inverses. They're just two different matrices. So, all right. So we have to multiply this row times this column. 8 times 3/17. Now, remember, when you multiply a number times a fraction, really this number is 8 over 1 if we wrote it as a fraction. We don't ever write over 1 because that's really not necessary. But we multiply 8 times 3/17. You just multiply straight across. 8 times 3 is 24. 1 times 17 is 17ths. So 8 times 3/17, you just multiply the top number and leave the fraction. 24/17. So let's put that here. So that's 24/17 plus the second numbers, 7 times 1/17. Let me make sure I wrote that down right. Correct, by the way, just to make sure. Yeah, the only negative was the 3 up there. Okay. Plus 7/17. 7 times 1. Now let's do this one over here. 8 times the negative 3/17. So that's negative 24/17. And then 7 times 4 plus 28/17. Well, I'll tell you, if we just simplify what we've got, 24/17 plus 7/17 is 31/17. That's not 1. Negative 24/17 plus 28/17 is 4/17. That's not 0. This is not the idea. We already know these are not inverses of each other. We don't even really have to finish it because this should be 1 and this should be 0. So we can stop right there on this one, go back to our problem and say, no, A and B are not inverses because this is not giving us the identity matrix. So let's check that. Good work. Let's look at another one. Okay. Are these inverses? All right, let's start over. If we multiply negative 11 times negative 3, 2, 7, all right, times negative 7/71, 3/71, 2/71, and 11/71. All right, so we're dealing with really weird fractions. You've probably never dealt with a fraction that had 71 as a denominator before, but it's not any harder than any other fraction. We're going to take negative 11 times negative 7/71. Remember, all we have to do is multiply the top. Negative 11 times. These are negative times a negative, so this is a positive, right? So that's 77/71. Okay, a little weird, but that's all right. Then the second number times the second one in the column, negative 3 times 2. So we're adding that, but it's a negative. So negative 6/71. Okay, that's not bad. We'll be simplifying that down here. Let's go over here. The second number, negative 3 times negative 3. Well, that's a 9/71. Notice we don't even have to really pay attention to what the denominator is because we're just multiplying the numerator times this number over here. So now, oh, wait, I did the wrong one, didn't I? I'm supposed to do the first one times that. Wait a minute. Don't want to get myself mixed up. I'm doing this row and this column. So I have to do the negative 11 times the negative 3. So that's 44. It's a positive because, again, it's a negative times a negative. And then this one, and I'm adding to it negative 3 times 11. So that's a negative. We're going to subtract it now. So minus 33/71. Make sure we got that right. 44 Negative 3 times 11, negative 33. All right, let me double check.
Are you
Make sure.
sure it's 44 and not 33?
No, I think you're right. I was looking at the wrong number. I was still stuck on the other number, 33. I was like, I think something's wrong there. I have multiplied the wrong number. 33. Yeah, 11 times 3. I don't know where I got a 4 stuck in my head. 33, because they're negative times a negative. And then this one's a negative times a positive. Okay. Thank you for correcting that. Don't let me sit there and do something wrong. Now we're going to do the second row times the first column, and then the second row times the second column. So 2 times negative 7, negative 14 71st. And then the 7 times the 2, plus 14 71st. Okay, now let's go to the second column. 2 times negative 3 is negative 6 71st. 7 times 11 plus 77 71st. All right, now we just need to simplify this. 77 71st minus 6 71st. Remember, when you're subtracting or adding fractions, you have to have the same denominator. Well, that's great because every one of these have the same denominator. So all we have to do is just add or subtract the numerators. 77 minus 6. That's 71. Oh, look, 71 over 71. That's just 1. 33 71st minus 33 71st. That's 0. Negative 14 71st plus 14 71st. That's a 0. Negative 6 plus 77. Well, that ends up the same as this, 71. Negative 6 plus 77 is 71 over 71. So these are inverses of each other because we ended up with the identity matrix. Once I knew how to multiply 11 times 3. Yes, they are inverses. Nice work. So that's how all 4 of these problems are. They give you 2 matrices and you have to multiply them together. So you're not having to find the inverse. You're having to check the inverse. So there's my stuff. That's what I want to screenshot. I want to show that I got them all right. Yay, 4 out of 4. All right, so close that. Go back here, paste, submit. All right, let's see what we have left. We've done the intro to inverses video lesson. Now we're going to do the last lesson, which is how do we know if an inverse even exists? Because not all matrices have an inverse. We looked at the problem that they weren't inverses, but that doesn't mean an inverse doesn't exist. There could be an inverse for the one that we checked, but this will tell us how to know if it even exists, because it may not exist. In fact, it will not exist for every matrix. All right, here we go.
Perhaps even more interesting than finding the inverse of a matrix is trying to determine when an inverse of a matrix doesn't exist or when it's undefined. And a matrix, a square matrix for which there is no inverse or for which an inverse is undefined, is called a singular matrix. So let's think about what a singular matrix will look like and how that applies to the different problems that we've addressed using matrices. So if I had and I'll do a 2 by 2 because that's just a simpler example, but it carries over into really any size square matrix. So let's take our 2 by 2 matrix, and the elements are A, B, C, and D. What's the inverse of that matrix? Well, this hopefully is a bit of second nature to you now. It's 1 over the determinant of A, 1 over the determinant of A, times the adjoint of A, and in this case you just switch these two terms, so you have a D and an A, and you make these two terms negative, so you have minus C and minus B. So my question to you is, what will make this entire expression undefined? Well, it doesn't matter what numbers I have if
Oh, let's talk about that. Because this is the key to knowing, is there an inverse? So with this inverse equation, 1 over the determinant, 1 over the determinant, that's not easy to say, times the matrix that's been rearranged, how could that possibly not have a value? How could that be undefined? Think about that for just a moment. Why would that ever be not able to be calculated? It's like, can't we always? Oh, Alora says 0 is the key. Alora is absolutely right. Because it's like, can't we always calculate the inverse? Not if the determinant is a 0. Because 1 divided by 0 is not a number, it's undefined. So if we had that and was going to multiply it by a matrix, we couldn't do that. 1 over 0. So anytime this determinant equals 0, no inverse will exist for that matrix. And he's going to get into how you can easily check that here.
If I have numbers here that make a defined, then I can obviously swap them or make them negative, and it won't change this part of the expression. But what would create a problem is if we attempted to divide by 0 here, if the determinant of the matrix A were undefined. So A inverse is undefined, if and only if, and in math they sometimes write it, if with 2 F's. If and only if the determinant of A is equal to 0. So another way to view that is, if a determinant of any matrix is equal to 0, then that matrix is a singular matrix and it has no inverse, or the inverse is undefined. So let's think about in conceptual terms, at least the 2 problems that we've looked at, what a 0 determinant means, and see if we can get a little bit of intuition for why there is no inverse. So what is a 0 determinant? Well, in this case, what's the determinant of this 2 by 2? Well, the determinant of A is equal to what? It's equal to AD minus BC. It's equal to AD minus BC. So this matrix is singular, or it has no inverse, if this expression is equal to 0. So let me write that over here. So if AD is equal to BC, or we can just manipulate things, and we could say if A over B is equal to C over D, right? I just divided both sides by B and divided both sides by D. So if the ratio of A to B is the same as the ratio of C to D, then this will have no inverse. Or another way, we could write this expression, if A over C, if I divide both sides by C and divide both sides by D, is equal to B over D. So another way that this would be singular is if, and it's actually the same way, if this is true, then this is true. These are the same, just a little bit of algebraic manipulation. But if the ratio of A to C is equal to the ratio of B to D, and you can think about why that's the same thing as the ratio of A to B being the same thing as the ratio of C to D. Anyway, I don't want to confuse you. But let's think about how that translates into some of the problems that we looked at. So let's say that we wanted to look at the problem. Let's say that we had this matrix representing the problem, the linear equation problem. Well, actually, this could be either one. So we have A, B, C, D times X, Y is equal to, I don't know, two other numbers that we haven't used yet, E and F. So if we have this matrix equation representing the linear equation problem, then the linear equation problem would be translated A times X plus B times Y plus B times Y is equal to E, and C times X plus D times Y is equal to F. And we would want to see where these two intersect. That would be the solution, the vector solution to this equation. And so just to get a visual understanding of what these two lines look like, let's put it into kind of the slope y-intercept form. So this would become what? In this case, y is equal to what? Y is equal to minus a over b minus a over b x plus e over b, right? I'm just skipping some steps, but you subtract ax from both sides, and then divide both sides by b, and you get that. And then this equation, if you put it in the same form, just solve for y, you get y is equal to what? Minus c over d minus c over d x minus c over dx plus f over y.
Should be
So
F
what do
over
you
D.
let's think
D.
about this. I should probably change colors because it looks too. Let's think about these two equations. What these two equations would look like if this holds, right? And we said if this holds, then we have no determinant, and this becomes a singular matrix, and it has no inverse, and since it has no inverse, you can't solve this equation by multiplying both sides by the inverse because the inverse doesn't exist. So let's think about this. If this is true, we have no determinant, but what does that mean intuitively in terms of these equations? Well, if a over b is equal to c over d, if a over b is equal to c over d, these two lines will have the same slope. They'll have the same slope. So if these two expressions are different, then what do we know about them? If two lines that have the same slope and different y-intercepts, they're parallel to each other, and they will never, ever intersect. So we could, let me draw that just so you get the... So if that's... so this top line might look, well, they both have, let's say these are, they don't have to be positive numbers, but this has a negative, I'll draw it as a negative slope. So that's the first line, and its y-intercept will be e over b. E over b, that's this line right here. And then the second line, let me do another color, would look something like, I don't know if it's going to be above or below that line, but it's going to be parallel. It'll look something like this. It'll look something like that, and that line's y-intercept, so that's this line. That line's y-intercept is going to be f over y. So if e over b and f over y are different terms, but these both lines have the same equation, they're going to be parallel, and they'll never intersect. So there actually would be no solution if someone told you, well, just the traditional way that you've done it, either through substitution or through adding, subtracting the linear equations, you wouldn't be able to find a solution where these two intersect if a over b is equal to c over d. So one way to view the singular matrix is that you have parallel lines. But then you might say, hey, Sal, but these two lines would intersect if e over b equaled f over y. If this and this were the same, then these would actually be the identical lines. And not only would they intersect in an infinite number of places, but still you would have no unique solution. You would have no one solution to this equation. It would be true at all values of x and y. So you can kind of view it when you apply the matrices to this problem. The matrix is singular if the two lines that are being represented are either parallel or they are the exact same line. They're parallel and not intersecting at all, or they're the exact same line and they intersect in an infinite at an infinite number of points. And so it kind of makes sense that the A inverse wasn't defined. So let's think about this in the context of the linear combinations of vectors. That's not what I wanted to use to erase it. So when we think of this problem in terms of linear combination of vectors, we can think of it like this. This is the same thing as the vector AC times x plus the vector BD times y is equal to the vector EF. So let's think about it a little bit. We're saying, is there some combination of the vector AC and the vector BD that equals the vector EF? But we just said that if we have no inverse here, we know that because the determinant is 0, and if the determinant is 0, then we know in this situation that A over C must equal B over D. So A over C is equal to B over D. So what does that tell us? Well, it essentially tells us that, well, let me draw it. And maybe numbers would be more helpful here, but I think you'll get the intuition. I'll just draw the first quadrant. I'll just assume both vectors are in the first quadrant. Let me draw. So the vector AC, let's say that this is A. Let me do it in a different color. So I'm going to draw the vector AC. So if this is A, and this is C, then the vector AC looks something like that. Let me draw. I want to make this neat. The vector AC is like that. And then we have the arrow. And what would the vector BD look like? What does the vector BD look like? Well, the vector BD, well, unless I could draw it arbitrarily someplace, but we're assuming that there's no derivative. There's no determinant. Have I been saying derivative the whole time? I hope not. Well, we're assuming that there's no determinant to this matrix. So if there's no determinant, we know that A over C is equal to B over D. Or another way you could view it is that C over A is equal to D over B. But what that tells you is that both of these vectors kind of have the same slope. So if they both start at point 0, they're going to go in the same direction. They might have a different magnitude, but they're going to go in the same direction. So if this is point B and this is point D, vector BD is going to be here. You might just want to think, if that's not obvious to you, think a little bit about why these two vectors, if this is true, are going to point in the same direction. So that vector is going to essentially overlap, is going to have the same direction as this vector, but it's just going to have a different magnitude. It might have the same magnitude. So my question to you is, vector EF, we don't know where vector EF is. Well, let's say, I don't know, let me just pick some arbitrary point. Let's say that this is E, and this is F. So this is vector EF up there. Let me do it in a different color. Vector EF. Let's say it's there. So my question to you is, if these two vectors are in the same direction, maybe of different magnitude, is there any way that you can add or subtract combinations of these two vectors to get to this vector? Well, no, you can scale these vectors and add them, and all you're going to do is kind of move along this line. You can get to any other vector that is a multiple of one of these vectors, but you can't get, because these are the exact same direction, you can't get to any vector that's in a different direction. So if this vector is in a different direction, there's no solution here. If this vector was, if it just happened to be in the same direction as this, then there would be a solution where you could, just scale those. Actually, there would be an infinite number of solutions in terms of x and y. And then, but if the vector is slightly different in terms of its direction, then there is no solution. There's no combination of this line, of this vector and this vector that can add you up to this one. And it's something for you to think about a little bit. It might be obvious to you, but the other way to think about it is when you're trying to take sums of vectors, any other vector, in order to move it in that direction, you have to have a little bit of one direction and a little bit of another direction to get to any other vector. And if both of your kind of ingredient vectors are the same direction, there's no way to get to a different one. Anyway, I'm probably just being circular in what I'm explaining. But that hopefully gives you a little bit of an intuition of, well, one, you now know what a singular matrix is. You know when you cannot find its inverse. You know that when the determinant is 0, you won't find an inverse. And hopefully, and this was the whole point of this video, you have an intuition of why that is. Because if you're looking at the vector problem, there's no way that you can find that there's no solution to finding a combination of the vectors that get you to that vector, or they're an infinite number. And the same thing is true of finding the intersection of two lines. They're either parallel or they're the same line if the determinant is 0. Anyway, I will see you in the next video.
Okay, don't let that overly confuse you with all the vector talk, because I'm gonna try to simplify that for you just a little bit. Let me put this up on the screen. So in our notes about inverses, we need to put it's undefined if determinant equals 0. And we can do the
if with two F's. If and only if. That's what two F's is. If and only if the determinant is 0, then it's undefined. And I'll close that parenthesis here. So that's when we don't have an inverse. And what he's talking about with the vectors is if we had two different lines that are created by a matrix, and that'd be by taking like AC and BD as separate matrices, you'd have two different lines. If those lines are the same slope, and that's the second one right there, then there's no inverse. That's what he's basically saying. If they have the same slope, if the lines are on top of each other, no inverse. But if it's graphed where you have two different lines or more, maybe four different lines, then it does have an inverse, but not when it's the same line. And we haven't really studied vectors, so I don't want to get too deep into that and lose you, but that's the main point. If it's the same slope, the two vectors that they create, if they separate those, if it's the same slope, no inverse. And that only matters because we have a quiz that talks about that. Let's look at our last thing. We're looking a quiz. Oh, determine invertible matrices. Let's look at that assignment real quick. The one that goes with this video that we just looked at. And then we're going to look at the quiz real quick too. So let's go. Okay. So it gives us a matrix. It says if this was a systems of equations matrix where it's 2x plus 6y and negative 8x plus 4y, because matrices can be systems of equations, equals whatever, B1 and B2. It says then you could write this as systems of equations, like y equals, right? We can rearrange that, and these would be the actual equations, y equals. So it says, does the system has how many solutions? Does it have one solution or zero or infinite solutions? And does it have an inverse or not? Does or does not? Well, remember what we just talked about. If they have the same slope, do these have the same slope? No, this has a slope of negative 1/3, and this has a slope of 2. So these are two different lines, which means somewhere they're going to intersect in one place, right? Remember, that's what's true about lines. If they have different slopes, if this has a negative 1/3 and this has a slope of 2, there's only one place they're going to cross. If we have two lines that have the same slope, maybe they will never cross if these are parallel to each other. No solutions. Or if we have two lines that are exactly the same slope, infinite. That's the only possibilities with lines, right? Either they have infinite number of places they touch, no places they touch, or one solution. So that's what this is asking. How many solutions does this have? Well, this has different slopes, so it has one solution. And since it has one solution, it does have an inverse. If you want to check does that have an inverse, you can do that A times D minus B times C. 8 minus negative 48. That's 56. That's not 0. So it does have an inverse, right? As long as that's not 0, AD times BC, that tells you there, oh, it does have an inverse. Check. Yes. Here's the next one. It just gives you a matrix, which again, you can check right there to see if it has an inverse. A times D minus B times C, 12 minus 24. This does have an inverse. So if it does have an inverse, it can't be this one. It has to be this one because it has an inverse. Because A times D minus B times C is not 0. So it must be different slopes. So yes, it has an inverse. Remember, it would be the exact same lines if it did not have an inverse. Check. So that's why it helps to know what he was talking about with vectors. Because if this equals 0 when we calculate it, it must be this one. This one just has you figure out what is the determinant. Negative 32 minus a negative 24. Well, that would be what? Negative 8. So yes, it has an inverse. Oh, I didn't get the answer right. What did I do? Negative 32 minus. Oh, that's a 32. I calculated wrong. That is 0. Yep. That's right now. I improved my answer. And then there's another one where it gives you the matrix and the equations. These have the exact same slope. So it'll either have 0 or infinite solutions depending on if they have the same y-intercept. And it does not have an inverse. There you go. All right, let's look at the quiz that we have this week because that's our last thing we need to check out. Okay. This says, what's the image we obtained when we perform this transformation? All this wants you to do is multiply those two together and give the answer. That is a 3 by 3 and a 3 by 1. So the answer is a 3 by 1. Multiply those together. That's all you have to do on number 1. Multiply these two matrices. Same thing. What is the image we obtain when we perform the transformation? If you perform a transformation, that means you're multiplying them together. Multiply those together. Get the answer. What's the determinant? There you go. AD minus BC. Does this have an inverse? Well, take AD minus BC. And what is the inverse? Here's the one we actually calculate the inverse. Where you take 1 over the determinant times swap A and B and do that multiplication. You got to do that on paper. That's going to be really hard to do in your head. And look, if it's a fraction, type it in decimal form. So you need in a calculator to convert it to a decimal. So this is a bit more work. You got to do most of these on paper. Just to find that inverse, you got to go through the steps. So, all right, guys. I know this one's deep this week. We got to, because you got to stop and think. You can't rush through that or you'll mess it up. It's not necessarily difficult. You just can't rush through it. Take your time. Do it right. So, and I'll check and see how many times you can do the quiz. I may need it. I probably want to give it a second or third attempt. Yeah, you have 3 attempts. You can try the quiz 3 times. Just because I know it's easy to make a little mistake, and that may drive some of you crazy. So I want you to have a chance to redo it. So you have 3 attempts. So, all right, guys. Any questions? You probably have a lot of questions, but you probably need to try this first and get a little practice with it, so you'll know exactly what your question is. But anyway, I'm here Thursday because Friday's an A day this week. So if you need help, come back Thursday. If your grade's below 70%, I'll see you Thursday. But otherwise, you're free to go, but you can hang around if you need help with anything. So we'll see you guys Thursday or next Tuesday.